Hello students, today we will study the second unit of the fifth semester, which is on the topic carboxylic acid derivatives, carboxylic acids and their derivatives. So in this we will be studying about the introduction and the nomenclature of carboxylic acids and their derivatives, physical properties, preparation, properties or reactions of carboxylic acids, reaction of the derivatives of carboxylic acid, and then finally the uses of both of them. So what are carboxylic acids? They refer to the class of organic compounds which have carboxyl group, not carbonyl, but a carboxyl means a carbonyl and a hydroxyl group. General formula is RCOOH, and these are the examples. Now, when when the OH group is replaced by a halogen, it is called as acyl derivative. When it is replaced by an anhydride group, it is called as acid anhydride. When it is replaced by OH is replaced by CONH2, it is called as amide. When it is replaced by OH group is replaced by OR 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 dash, then it becomes ester. So, what are carboxylic acids? They are named by replacing the final E of the name of the corresponding alkane with the oic acid. So, if there is alkane or methane, so the corresponding acid will be called as methanoic acid. And carboxylic carbon is assigned the position 1. Okay, like this. Then we see what are acyl chlorides. Acyl chlorides means the final ic acid is replaced by ill chloride. For example, ethanoyl chloride, because there are 2 carbons and 3 carbons, so it is propanoyl chloride. Similarly, then acid anhydrides. They are named by dropping the word acid from the name of the parent carboxylic acid and then adding the word anhydride. So, ethanoic anhydride, ethanoic propanoic anhydride, benzoic ethanoic anhydride. Then talking about next, that is amide. So amides that have no substituent on the nitrogen atom are named by replacing the oic acid from the parent carboxylic with an amide. For example, now you see substituents on the nitrogen atom of the amides are named and the named substituent is preceded by N or NN dash. For example, this ethanamide, propanamide, benzamide. So if there are 2 methyl groups attached to the nitrogen, it becomes NN dimethyl propanamide. Similarly. Then coming to the next derivative, that is ester. So ester is named after replacing the carboxylic acid with an OH. So when ill is replaced by OH, the portion of the name derived from alcohol comes first, like methyl ethanoate, ethyl methanoate. So whatever portion is derived from the alcohol, so that comes first. Then methyl ethyl ethanoate. Then coming to the physical properties. So they are mostly colorless liquids at room temperature and they have a characteristic pungent smell and a sour taste. These are the common carboxylic acids with their melting boiling points and density. So let us see the boiling point. So if you compare the carboxylic acid boiling melting point with that of alcohol to that of aldehydes to that of alkanes, so you find that the carboxylic acids have the highest melting and boiling points. Why? Because of intermolecular hydrogen bonding, and these hydrogen bonds are more extensive than those in alcohol. That is why they are even more they have even more higher boiling point and melting point than alcohols. Then coming to the density. So their density decreases with their increase in relative molecular masses. Only methanoic and ethanoic acids, they are dense than water at 20 degrees. Why? Because of the closer packing of the smaller molecules in the liquid phase. Then looking at the solubility. So carboxylic acids of lower molecular mass have lot of solubility in water. They are highly soluble. Why? Because they are polar and then they can also form strong hydrogen bond with the water molecules. The first 4 carboxylic acids are actually miscible in water. And the length of the hydrocarbon portion is more whenever the, like I told last time also in carbonyl compound also, the more the hydrophobicity, the less is the solubility in water. Same goes with carboxylic acid. Now there is an example like rank the following compounds in decreasing order of solubility in water. So there are 3 examples given. So we will see that the most solubility will be for the smallest member. Then coming to preparation using hydrolysis of nitriles or cyanides. So the mechanism is basically nucleophilic addition reaction of aldehyde ketone with HCN, hydrogen cyanide, or maybe by acid hydrolysis or alkaline hydrolysis of their alkane nitriles, which produce carboxylic acid or carboxylic ion respectively. So this is the mechanism given. Now, the acid hydrolysis, it results in a carboxylic acid which has one carbon more. So there is a chain increment reaction. Why? Because the cyanide group is introduced into the main compound. So you can see where, here when cyanide group hydrolyzes, it gives an acid group always. Then through hydrolysis of esters. So this gives the parent carboxylic acid and alcohol by boiling under reflux with dilute HCl or H2SO4. Now the acyl chlorides or acid anhydrides or esters or amides, they all can be hydrolyzed to give the corresponding carboxylic acids. And the reactive derivatives, they react vigorously with water like acyl chloride. And the less reactive derivatives, they require more severe conditions to bring about the reaction. Then coming next is oxidation of alcohols and aldehydes. So aldehydes and primary alcohols, they can be oxidized to carboxylic acid by using the reagent which one came for an acidic medium. This is another example. Next, we see the oxidation of alkyl benzene. So primary and secondary alkyl groups, but not tertiary, they react directly. They directly attach to benzene ring. They are oxidized to carboxylic acid using this reagent in the basic medium. Normally, this oxidation takes place initially at the benzylic carbon. Why? Benzylic means carbon attached to the benzene ring, not a part of the benzene ring. Why? Because alkyl group longer than methyl group, they are ultimately degraded to benzoic acids. Then next is the reaction of the carboxylic acid, that is acidity. It is a very important example. So carboxylic acids, they are weak acids and their acidic properties are due to the presence of ionizable hydrogen atom. So what happens is that in water, carboxylic acids, they break as carboxylate. Like in case of acetic acid, acetate ion and H plus ion. And the acid strength, it is shown by Ka, which is the acid dissociation constant. And pK is usually used for convenience because pK is related to Ka through negative of log. So smaller the pK value, more stronger is the acid. Next important parameter is the resonance effect, which affects the reactivity of carboxylic acids. So the greater the stability of the carboxylic acid is attributed to resonance stabilization of the carboxylate ion. You can see over here in the figure how the carboxylate ion, because of conjugation, because of resonance stabilization, it is getting stabilized. By the resonance effect, the ethanoate ion can be stabilized by spreading the negative charge over 2 oxygen atoms. And no such stabilizing resonance structure for alkoxide ion. If you compare it with alcohols, there is no such resonance stabilization. That is why alcohols are more reactive and less stable. Then carboxylic acids are much acidic than alcohols. Why? Because of the formation of the more stable conjugate base. Next is the inductive effect. So inductive effect, if you see, if we compare ethanoic acid with ethanol, you see the inductive effect is more in case of ethanoic acid. That is why, because it is a stronger acid because of the inductive effect. Because of the inductive effect, what happens is that the carboxylate, the carbonyl group, it withdraws electron density toward it, so the OH bond strength is lower, and so it is easier to remove the H plus from the compound. Whereas in case of ethanol, that is not possible. That is why the OH bond strength is more, and it is difficult to lose an H plus. Both the compounds, they contain highly polarized OH bond due to difference in electronegativity. The greater acidity of ethanoic acid is due to the presence of powerful electron withdrawing carbonyl group. So you see the resonance structures for the carbonyl group. The carbonyl atom of the ethanoic acid, it bears a large partial positive charge and exerts a powerful electron withdrawing inductive effect to hydroxyl oxygen atom, making the hydroxyl hydrogen atom more positive, and the proton dissociate more easily. And the electron withdrawing inductive effect of carbonyl group that only stabilizes the carboxylate ion, and that is why the carboxylic acids are stronger acids than alcohols. Next, let us see the inductive effect of other groups. So one is electron withdrawing, other is electron releasing group. So let us see the electron withdrawing groups. So what happens is that whenever an electron withdrawing group is present along with the carboxylic acid, what it does is that it increases the acidity of the carboxylic acid, like just we saw. So if you compare ethanoic acid with, or this is acetic acid with chloroethanoic acid. So because there is an electron withdrawing group, so it will stretch the electron density towards itself, so the OH bond strength will be lesser, and so it is easier for the compound to lose the H plus. So this one, the right one, is more acidic. Chlorine atom, it withdraws electrons from the carbonyl group and oxygen, making the hydroxyl hydrogen more positive than that of the ethanoic acid. And this also stabilizes the chloroethanoate ion to great extent. Now, if you see the effect of the electron withdrawing substrate on the acidity of carboxylic acid, so there are a lot of examples given. So if we increase the number of, if we replace the hydrogens of the methyl group with each time with the chloro group, and we compare the pKa, or the measure of acidity. So you see the lesser the pK, the more stronger it is acidic. So you see the trichloroethanoic acid, it is highly acidic. Similarly, if you compare among halogens, so iodine, bromine, chlorine, and chlorine. So we see that the one with fluorine is highly electronegative. Why? Because firstly, the greater the number of electron withdrawing group, the stronger is the acid, and the more electronegative atom, the more electronegative halogen atom, it makes the acid more stronger. The further away of the substrate from the carboxylate, the weaker. The second thing is that if you compare, like if all of them have same number of halogen atoms, or the same, even the halogen atom is also same and its number is also same, then what happens? Then we have to see how far it is from the carboxylate group. So the further it is from the carboxylate group, the weaker is the effect, and hence the weaker is the acid. Last, we come to the electron releasing groups. So the presence of electron releasing groups, what it does is that it reduces the acidity of the carboxylic acid. For example, if we see methanoic acid or formic acid, and we see acetic acid. So what happens is that because now here the group is what kind of group? It is electron releasing group. So methyl group is electron releasing. So it decreases the acidity because it is anyways concentrated the electron density over the OH bond, so it is difficult for the OH bond to break. So that is why acetic acid is a weaker acid than formic acid. So again, same thing, electron releasing alkyl groups, they release electrons towards the electron deficient carbonyl group, thus reducing its charge. Reduce the positive character of the hydroxyl hydrogen atom, and so it dissociates less readily. And this also intensifies the negative charge on the carboxyl group, and that is why it destabilizes the anion, the ethanoate anion. This is how it is shown how the ethanoate ion is destabilized by the electron releasing effect of the methyl group. Now there is a question over here that you have to arrange the following aryl carboxylic acids in descending order of acidity, and also we need to explain this order. So there is one carboxylic with no other groups, there is one carboxylic with an electron releasing group, and there is a carboxylic with an electron withdrawing group in vicinity. So let's see. So if we see, of course, the one with electron releasing will be the least electronegative, or the least acidic. And the one with an electron withdrawing group, that is chlorine, it is going to be most electronegative. So what remains in between them? The group which has nothing, neither electron withdrawing nor electron releasing. Now we understand why. So see, the chloro derivative is more acidic than the one which has no other groups. Why? Because it contains chlorine substituent, which is an electron withdrawing group. So what it does, it exerts minus I effect, a negative inductive effect to the conjugate base, and hence it stabilizes the carboxylate ion which is formed. Now, if we compare the second and the third one, so the methyl derivative and the one which has no other substituent, the methyl derivative is less acidic. Why? Because it contains a methyl group, which is electron releasing group. So what it does, it exerts a plus I effect to the conjugate base, and hence it destabilizes a carboxylate ion form. So that is why this kind of questions, this kind of conceptual questions will come, and we have to answer it accordingly. So students, I think that is all for today. We will take up this topic in different parts. So we will come up with the next second part of this lecture very soon. Thank you.